Hi everyone, and welcome to today's webinar, which is titled Better Reinforced Soil Analysis with LimitState GEO. I'm Tom Pritchard, the host for today's session, and I'll be passing you over to our speaker shortly and also rounding up at the end. Hopefully today you'll come away with an overview of how LimitState GEO's engineered element material works and how it can be applied to a wide range of soil reinforcement problem types such as soil nails and geosynthetics. The webinar itself is going to run for approximately 45 minutes and will include a few minutes at the end for questions. You can post these at any time via the chat functionality that's present in the webinar interface that should hopefully be in front of you. And we'll try to answer as many of your questions as we can during the webinar, but this isn't always possible. But we do reply to questions that we don't cover in the few days that are following the webinar itself. So I'd just like to introduce you now to our speaker for today, who is Dr. Colin Smith, and he is the LimitState GEO Product Manager.
Okay, thank you, Tom. So to start off the seminar, we'll have a look at a few slides showing the range of problems types that can be solved by LimitState GEO. So as you're probably aware, LimitState GEO is a general-purpose ultimate limit state software able to determine the collapse state for any problem geometry and able to model slopes, retaining walls, structural elements, and soil reinforcement, as shown by some of these examples. So our aim today is to focus on soil reinforcement. So in terms of the content, we'll be looking at a little bit of background to reinforced soil analysis, geotechnical analysis software, and then we'll look at a couple of examples: soil nail, reinforced slope, and a reinforced embankment. And we'll also take a quick look under the hood of the software to see how it works. So to this end, I'll primarily be using the software directly to illustrate the key points, but I'll make use of a few slides at the beginning and end for introductory and summary. And as this is a short presentation, the main aim is to give you a flavour of what the software can do, and there won't be time to get into the details of all the functionality. However, there will be time at the end for questions, as Tom has stated. So a little bit about LimitState itself. Company's mission is to provide engineers with powerful software for limit state analysis and design, leveraging the latest state-of-the-art algorithms and optimization technology. And this innovative approach has generated a client base covering over 30 countries worldwide. So where does our software fit in? Well, we focus on tools for ultimate limit state analysis. So this allows us to provide products that combine the speed and ease of use and simplicity of traditional methods with the flexibility of the finite element methods to handle any problem geometry. And typically, the only parameters we need are the cohesion, friction, and unit weight of the soil. So that's enough introduction. Let's try out the software. So quick introduction to soil reinforcement and types. So soil reinforcement works primarily by adding you can consider it working by adding tensile strength to the soil, or equivalently transmitting load from one part of the soil body to another through a tensile element. And such reinforcement might be one-dimensional or two-dimensional. So your one-dimensional reinforcement would be soil nails or steel strips, and 2D reinforcement typically geogrids or geotextiles. Now, LimitState GEO is a two-dimensional problem, so it can model the two-dimensional reinforcement directly, but you need a slightly special approach to model one-dimensional reinforcement to allow soil to flow past the nail if needed. And there are a large range of applications for soil reinforcement. I've given 3 examples here: one of a nailed slope, one of a reinforced soil wall with concrete panels, and one of a reinforced embankment and soft ground. Now, in terms of analysis, if we look at how we might a classical approach to slope analysis with reinforcing elements, typically it's a limit equilibrium approach. You might use the method of slices. So you pre-assume a slip surface, and you can look at the equilibrium or forces along that slip surface in terms of shear and normal force and available resistance. And if you've got reinforcement within the soil, then what you can do is say that you can calculate the additional force required for that slip surface to occur. It's going to have to pull the reinforcement out of the soil behind the slip surface. You can calculate that pull-out force and then say that that can be applied to that slip surface for stability. And it may be that the reinforcement pulls out of the soil behind the slip surface, or actually it stays within the soil there and gets pulled out in the body of soil at the front. But either way, the relative interaction is the same, and we can model that in a fully general way. So we're going to have a look at how that works in LimitState GEO. Before that, we'll have just a quick recap on how the software works itself in general. So LimitState GEO uses a numerical technique called discontinuity layout optimization. It's a method that is a rapid and direct means of analysing the collapse state. Rose from a research project carried out at the University of Sheffield and was published back in 2007 in the Proceedings of the Royal Society. And since then, been a lot of publications, further publications. To explain very simply how it works, we'll look at a very simple example. So we have a block of soil here with a fixed boundaries to the left of the base and a load at the surface. Instead of populating it with elements, this domain in a finite element approach, in this approach we don't populate the domain with nodes. And essentially we connect every node to every other node with a potential slip line. So here we've got 12 nodes. So there are 12 times 11 over 2, 66 connections. And then we use optimization to pick out of that set of potential slip lines the critical ones that form the critical collapse mechanism. So out of those 66 there are actually 6 slip lines which form the critical collapse mechanism that dissipates the least energy, and the software can find that very straightforwardly. Now normally we're solving problems with maybe 500 or 1,000 nodes, so potentially a million potential discontinuities, and the software is able to pick out of that very quickly the critical collapse mechanism. So the more nodes you put into the problem, the more higher the accuracy. So when we apply that to reinforced soil, we essentially include a special one-dimensional reinforcement element in the software, and in a fully general analysis, we may have multiple wedges of soil moving in different directions relative to the reinforcement. So we cannot think about internal and external stability, particularly. We have to make sure that we model this in a fully general way. And that's exactly what's done in the software. It's modeled in a fully general way, but still adopting the same mechanics principles as in a classical analysis. So, for example, in this slide, we've got reinforcement pull out from the soil in this area here. And we've got differential movement between soil and reinforcement here, 2 different wedges moving past. That's all captured. And here we've got the reinforcement actually pulling out of the wall in this case. So we can capture pull out at this end here, or indeed rupture of the reinforcement itself. Now, the discontinuity layout optimization method has been verified against a wide range of closed-form solutions and benchmarks. Over 100 results can be viewed on our website. Specifically for the reinforcement, it's been verified against a number of papers in the literature. This just shows one slide of the DLO results, which are the black squares, against results in the literature from Leshinsky 1987 for a particular for an embankment problem, reinforced embankment problem. There's also a growing bibliography or literature on the use of DLO to model reinforced soils. You can download a list from our website. This is just some of the papers that have been used to model reinforced soil types. So we're going to look in detail at how the reinforcement is modeled in the software. So we'll first just recap on the sort of mechanics. If we have a reinforcing strip here, and it is subject to a tensile force, then that is dissipated into the soil by shear forces along the top and the base, or around the circumference of the reinforcement, depending on what it is. So in this case, if we think of a soil nail, it's a one-dimensional object, so the dissipation, the shear stress is applied on the circumference of that. In an undrained soil, we'd assume that that's equal to alpha by Cu, where alpha is an adhesion factor. And if we've got cylindrical reinforcement, then we'd multiply by pi d, where d is the diameter of the nail, to get the actual pull-out force per unit length. And this is a parameter that we need to put into the software to tell it how that interaction of the soil nail works with the soil. For a drained soil or frictional soil, then that shear stress at failure is often assumed to be alpha times the normal stress times tan of the angle of friction. So that's your kind of classical calculation, and therefore the pull-out force for a soil nail will be the circumference, again multiplied by this, where we assume that this is the average normal stress on the nail, and quite often that's taken as a function of the prevailing vertical stress. Now all of these parameters have to be specified per unit width into the diagram, so that means if you've got one nail per meter, then you put that number in. If you've got 2 nails per meter, then you can double that number, and so on. But it's probably clearest just to illustrate that with the software. So if I just bring that up. So I'm going to run this model here. So what we've got here is essentially a block of soil here, a rigid block here like lumber concrete, our reinforcement element here in the soil, and then it's connected to another reinforcement element which is rigidly embedded in this lumber concrete. And what we're interested in is the force required to pull this length of reinforcement out of the soil. So if you haven't seen the software before, I'll just kind of recap on the layout of the screen. So we've got a number of buttons down the side to do with modifying the geometry of the problem and viewing it. Buttons on the top looking at the solution. We have a thing called a property editor on the right, so anything I click on in the software, its properties will appear over here, and its geometry will appear down here. And we have the main screen in the middle here. And we also got a materials explorer here, which show the materials that are currently available to us in the problem. Some of these are built in with a padlock on, others are user defined, and we can define more materials in this case. So if I first click on this soil here, look at the property editor here, it says it's a soft clay and it's got an undrained strength of 30 kilonewtons per meter squared. If I click on the engineered element, that's this one here, oops. I'm just trying to get that, yeah, highlighted. I can see its properties here. We'll ignore the top and bottom components for the moment, come back to those later on. It says it's reinforced element 2, and it has these particular properties. So what we're saying is a pull-out factor of 10 kilonewtons per meter, and that is equivalent to approximately a 10 centimeter diameter nail spaced at 1 meter intervals into the diagram if they're embedded in that clay of strength 30. So if we use that simple formula on the previous slide, that's what we'd get roughly. So essentially, this has a pull-out strength of 10 kilonewtons per meter per unit length of nail. The nail itself has a length of 2, so if I look at the geometry editor down here, starts at a coordinate x of 2, ends at 4, so it's 2 meters long. So if I solve the problem, I should get an answer of 2. Just going to ignore that little warning. And indeed, I get an answer of 20. So that's what we expect. And we also get a little graph of the axial force, which is going to build up from 0 at this end and up to this end to a value of 20. Again, as we'd expect. Now, if I were to change the property of the soil nail, I can also access it from the Materials Explorer. It's called Material R2 or Nail R2. If I change that to 20, then I'm doubling its pull-out strength per unit length. So if I solve this again, just ignore that, I get a result of 40, which is what I'd expect. And I can keep doing that, but I'll put in a value of 100 here, so normally we'd expect to get an answer of 120. Again, I'll just mention this in passing. So this is a diagnostics facility, so built into the software. It will analyze the problem, you'll do a pre-analysis or pre-assessment of the problem you're analyzing, and just flag up some useful information to you about what you've set up to make sure you can check it's as you expected, and might give a warning where it thinks that you might have perhaps forgotten something here. In this case, I can freely ignore this because I'm happy with the way the model is set up, but it's relating to whether this nail itself connects to a rigid boundary. If you recall, I put in a value of 100, and I would expect to get 2 times 100, but I actually get 120. And the reason for that is that it's not 200, because what I'm doing is I'm not failing the pull-out between the pull-out force of the nail itself. I'm actually failing the soil around the nail. Now, if you recall, the soil around the nail, if I just click on it, just don't do that, has a strength of 30. And so if this reinforcement were actually a plane, the force required to pull that out. So if we had hundreds of nails all essentially adjacent to each other, so we formed a plane, the maximum force that we can pull out at is going to be that shear strength of 30 times 2, because we've got it above and below, multiplied by the length 2 there, which comes out as 120. So physically we cannot get any more pull out than 120 from that soil, even if we had contiguous soil nails all the way along. So that's why the software is giving us that answer. Finally, I will just show you that we can also fail the nail itself, or the engineered element itself. So we have here a rupture strength, which is currently set at 1E30, which is a way of telling the software it's infinite. If I set that to 60, what I'm saying is that if the tensile force builds up to 60, it will just yield at that point. And you can see I've actually got that solution of 60. So it only allows the stresses to build up to 60 and won't go higher than that. And what happens now is we haven't got pull out of the reinforcement at this end. Basically, the reinforcement is stretching or failing in that case. Okay, so that's hopefully shown you how we model a one-dimensional soil nail in a sort of element test. We'll just jump back to the presentation. We'll just look at applying that into a problem of a soil nailed slope. So basically we're looking at a fairly steep slope in a soil with a cohesion intercept of 3.5, angular friction of 26 degrees. We've got 0.25 meter diameter nails. We're going to assume full interaction with the soil and a horizontal spacing of 1 nail per meter. If we take those properties, we can calculate the pull-out capacity of the nail per unit length. So it's going to have a cohesive element to it, which is this term with a C dashed in of 2.74 kilonewtons per meter, and also an element that relates to the surrounding normal stress on the nail. So this TQ value is that expression we saw earlier, and that needs to get multiplied by the assumed normal stress on the nail at any point to give you the pull-out force. So the software will calculate the sum of this and this value. And what it does is it assumes that the normal stress on the nail is equal to the nominal vertical stress at the level of the nail. Again, that's a typical assumption in classical limit equilibrium analysis. Where are we? Let's just go back to that. So what we'll do is run the software again, and so I'll just close that, and then open up the next example, which is the soil node slope, that one. So that's the model as I showed you in the previous slide. The soil, if I click on the soil here, you can see we've got that 3.5 and 26 for strength. The nail itself has this 2.744 and 0.383 value. And we have these pull-out factors. The software also models what we call lateral factors, and this accounts for the resistance of the nail or the reinforcement to moving in a direction normal or sideways to its orientation. Now, in classical limit equilibrium, that's just ignored. What I put in here is a very small value for the cohesive component of that. That will not add any significant resistance, but it just occasionally the analysis gives a result where the nails appear to float out of the soil, because if they have no lateral resistance, there's nothing to stop them moving. So if I solve the problem here, you see the failure mode that we have. What the software has found is quite a shallow failure, just shearing past the reinforcement. The reinforcement stays fixed and the soil just shears past it, and there's a bit of pull out of the front end of the reinforcement from that sliding wedge. So conventional analysis might consider two wedges further back, but this is in fact the failure mode that is most likely in this particular case. Now, the analysis that we've done, if I just explain that briefly, what we've done is a factor on load analysis here. And so we're asking the software the question, effectively, how much heavier does the soil have to be in this problem to cause collapse? We can set that in different ways. We could ask it the question, how much does the surface load have to increase to get collapse? But in this case, we've just picked the weight of the soil. If I click on the result here, I get a little summary, and it basically says you need to increase the weight of all these blocks by this factor 1.003, so almost hardly change it at all, to give me this value here. And these are all hyperlinked, so I can click on them and it shows me which blocks are being increased. So basically we're saying increase the weight of everything, and see if we need to get to collapse. So the fact we're getting an answer of nearly 1 means that this system is just on the point of collapse, as it is. Now we can look and see what would happen if I make these nails shorter. So what I'm going to do is just select. Oops. If I hold the control key down, I can select multiple parts. If I click on this ortho button, I can drag these inwards. So I'm just going to shorten them a bit, and I'm going to do the same with this element here. Oops. Move that in. So I basically shortened all the nails. Quite clearly that doesn't look right. They don't look long enough. And if we run the analysis, the software it concurs and says basically we're going to fail mostly around the outside of that, and effectively he's going to move almost as a rigid block, and we get a much reduced factor on load, which basically says this slope is massively under-designed. The unit weight of the soil would have to drop to half its value. It would be stable if the soil weight was 7 kilonewtons per meter cubed rather than 7. So it's clearly unstable. And you can click on these elements if you want to view the tensile stresses that are being produced in the element. And you can see obviously they go to 0 at either end because they're free ends. Okay, so we'll jump back to the presentation. Now, this analysis has been validated. I'm showing you one slide here where in fact the software was forced to adopt a two-wedge analysis and told it had to find a failure mechanism along these two wedges, but all the angles were varied and it got exactly the same answer as a classical analysis. So we can get the same as a classical analysis, but as you've seen with the software, it can pick up many different types of wedges, multiple wedges, and therefore it's going to find a much more accurate answer in terms of collapse. So to summarize, if we're modeling one-dimensional soil nails, we've got a setup in the software that allows the soil to flow past the reinforcement. Effectively, it just models the energy dissipation along that one-dimensional element. It's been calibrated against two-wedge analysis, and if you're adopting this approach, you need to calculate your pull-out coefficients, TC and TQ, from the nail geometry and soil properties, as we saw in a previous slide. You need to put in these lateral coefficients that we have, but typically we're going to set those close to 0. And you need to put a tensile rupture strength for the 1D element. And leave it at that. There is an option to put boundary materials above and below the element. That's required for two-dimensional reinforcement, but in one-dimensional reinforcement, we don't put that in. So we'll now look at two-dimensional reinforcement. So this is, for example, geotextiles or geogrids. So again, if we look at how this works, if we've got a sheet reinforcement, we can model it as a flexible engineered element which has 0 bending strength, and but the pull-out mechanics are very similar. We've got shear stresses above and below the reinforcement sheet, and that determines the force required for pull-out. So in this case, what we do is we directly specify the interface properties. The software allows differential shearing above and below the reinforcement if that's what happens in the analysis. The normal stresses are inherently determined by the analysis, and if we specify infinite pull-out and lateral resistance, it means that failure is forced to happen on the interfaces with the planar reinforcement, which is what we require. And we can also put in a tensile rupture strength for the reinforcement if we wish. So if I pull up the software again, so let's shut that and open the next example. So this is going to be this one. So looks very similar to that previous one, but if I click on the reinforcement, well, I click on the soil, we've got a clay. This time it's got an undrained shear strength of 50. And if I click on the reinforcement here, we can see that it has a length of 1.5 meters, runs from 2 to 3.5 here. We've put an infinite pull-out, infinite lateral, which is what we require for planar reinforcement. In this case, I've also given it an infinite rupture strength, so we're going to assume it's not going to fail in that way. And its interaction with the soil is going to be controlled by what's on top and at the bottom. At the moment, we've put no materials there, 0 materials assigned, so we've got full interaction. So we should expect the pull-out force here to be the length of the reinforcement, which is 1.5, times 2, because we're going to interact above and below. So that's 3, multiplied by the shear strength of the clay that it's sitting in, which is 50. So we should get 150 as the result. So if I click solve, we indeed get a load of 150 as we expect. Now we can change that. So if we think that the interaction between the reinforcing element and the soil is not the full strength of the soil itself, we can put an interface element. Now I've pre-created ones here. Here's one called interface above. This is what we call a derived molecular material. Basically it says mirror exactly the properties of a parent material, which in this case is the clay that we've modeled to surround the reinforcing element, this strength of 50, but reduce its cohesive terms by 0.9, so the Cu by 0.9, and any frictional terms by 0.9 as well. In this case we're modelling an undrained soil, so we're really only interested in modifying the Cu value. So we put 0.9 above, so I can, if I click on here, I can change the top element there. It says no materials assigned. If I click on this box, I get a choice of change, and I'm going to put interface above. And similarly on below, if I click change, I can add the interface material below. So if I zoom in on that, you can now see I've got slightly different coloured elements above and below. Oops. And those designate those materials. So essentially I've got 0.9 above, 0.6 below. So instead of 2 times 1.5 times 50, I should get 0.9 plus 0.6 times 1.5 times 50 as my solution. And indeed I do, I get 112.5. So I'm modelling the correct amount of shear force above and below that element. So that's effectively modelling a planar reinforcement. So if we look at an application of that, go back to the slides. We'll look at using that to model a reinforced embankment. So often we use sheet reinforcement for constructing embankment over soft soil. Sort of questions you might ask are, what slope angle is feasible for the embankment? How strong should this surface soil be? How high can we build the embankment? What sort of strength do we need for the reinforcement? We get all those answers from the software. Now your classical approach of analysing this sort of problem might be a slip circle method of slices approach, where you might model a log spiral in the embankment if it's a frictional soil and a circular arc in the soft soil below. But you're not going to capture all possible failure modes there. You might capture 1 or 2 critical ones, but you'll miss out on some others that may or may not be present in the problem. So we'll have a look at the software again. Just kill it one and open up again. So we're going to look at reinforcement embankment. So there we've modelled an embankment. So the surface soil, if I click on that and look at its properties, we've given it a cohesion intercept of 0.5, friction angle of 32, unit weight of 18. It's sitting on a soft soil which has got an undrained shear strength of 16 and a unit weight of 15. And the reinforcement we've put in, I'll click on geotextile here, we've put in these infinite pull-out and lateral factors. They're irrelevant for 2-dimensional properties, 0 bending strength, and a fairly low rupture strength of 25. Instead of modelling the full width embankment, I've modelled half the embankment, so I've got a symmetry line down the side. One thing that when you're modelling a reinforcing element right up to a boundary, the end of the reinforcing element is normally modelled as just free, so it's just sitting free boundary, and it's not rigidly connected to the boundary, so it's free to move. So if you're trying to model half the problem, that doesn't work because the reinforcement would clearly continue along, and what we want is a 0 displacement condition for the end of the reinforcement. So we can do that quite easily. What I've added here is a little short piece of reinforcement running parallel to the symmetry boundary, and I've put a frictionless material, if we look at it there, frictionless material on either side of it. So it's basically free to slide up and down, but any reinforcing element, engineered element that connects to any other one is rigidly connected. So essentially, this is now got zero displacement boundary condition at this point, but is free to slide up and down along that position. I wouldn't need to model that if I model the full width problem, but then I would have twice the computational cost. So if I solve that problem, and I'm using what's called a factor strength analysis here, so what I'm doing is I'm asking the software, what is a factor of safety on strength of my soils, or how much do I have to reduce the strength of soils by to get collapse? And if I click on that solution, what it's telling me is these were the original values of the soft soil and sand strengths, and they have to be factored down, or sorry, factored up by 1.234 to get collapse. Sorry, factored down by 1.234. So we've got a margin of safety of 1.234 on the soil strength here. They have to be reduced to these values to give us collapse. And we get a sort of slip circle type mechanism. You can see along the outer boundary of the failure, we're getting something that's quite akin to a slip circle. So you would get that from a sort of classical analysis. So we've checked this against slip circle method of slices results in the literature. We get a close agreement for this mode of failure. If I make the geotextile much stronger, so I put 250 in there, it's got a very high rupture strength, then I can basically, the critical mode of failure then becomes failure of the embankment edge. We get a slope failure there, the factor's gone up to 1.43, and that's because it's much harder to get that full combined failure to pass through that much stronger geotextile. And again, you would be able to get that in method of slices if you focused on the embankment edge. But if we then look at an issue where we might get a squeezing type of failure, so if the soft soil under the embankment is very weak, then if I just put a strength of say 8 in there, so I've halved the strength of the soft soil, then I tend to get a failure mode which is more akin to squeezing, where the soil is being squeezed under the embankment, and there's a more general squeezing type failure that's going on. And that would be quite hard to get with a sort of classical slope analysis or method of slices. And then just finally, if I revert that strength back to 16, and I'm going to change this top boundary interface to something a bit lower, 0.2. So we're almost assuming a low friction interface at the top, then we would expect to see a kind of wider failure on the surface, and that's what the software is coming up with. We're getting a wider failure mode here, where it's favouring a mechanism which allows a lot of sliding along this base, because we've made that a very low friction base, and we've now got a strength which is below, or a factor that's below 1, which means that this is an unstable model. So hopefully that's illustrated how we can use this two-dimensional element as part of a reinforced embankment analysis. You can of course use it in other problem types. So just to summarize, we've got a very generic implementation of planar reinforcement in the software. It's been calibrated against method of slices and slip circle analysis, and the recommended approach to modeling things like geogrids or geotextiles is to use these engineered elements with effectively infinite pull-out and lateral coefficients. So they're really only needed for one-dimensional modeling, one-dimensional reinforcement. Specify the tensile rupture strength and put in the correct boundary materials and interface materials above and below the element, so that will replicate your classical interface factors. So we're getting close to the end of the webinar, so we'll just wrap up with some conclusions. So hopefully you've seen that reinforcement modeling in the software uses the same mechanics as conventional methods, such as a two-wedge method, but it effectively allows us to model thousands of wedges in any type of collapse mechanism. Because they're modeled in a fully general way, there's no need to separately consider internal or external failure or pull-out lengths or reinforcement rupture. That's all just captured in the one analysis. The software will automatically search all possible failure modes every time you solve, so you don't have to look at specific ones that you perhaps normally would by hand calculations. And we can model both one and two-dimensional reinforcement. Hopefully you've also seen, while I've been using the software, that the workflow is straightforward, from adjusting the geometry to reporting. We didn't actually look at the reporting, but basically the software puts you in control. The user interface allows you to explore and change things very easily. You can solve quickly with one mouse click. And again, we didn't have time to look at that, but it's very easy to put in partial factors that correspond to Eurocode, for example. So it's very interactive, it solves quickly, so you can use it to answer what-if type questions, or just to get an initial exploration of a problem, to get a better feel for how it works, what's going to control the design, and then you can do the detailed design as well. And this one piece of software can, because it's fully general, can solve any ultimate limit state problem type. No need to put in idealizations or correction factors for non-standard geometries, and no need to learn many different programs. So that wraps up the webinar. We've got a few minutes left for questions, so I'll just pick out a few questions. Okay, so I got a question about, could I elaborate on the coefficients NC and NQ? When would you use them? How would you determine the values? So if I jump back to the software, so essentially, and in fact what I will do is I'll just pick out a soil layer problem. There we go. So if we imagine these are one-dimensional elements, generally we're concerned in classical analysis with those being pulled out of the soil, but if they were to move sideways, obviously you'd require a force to move them through the soil, or conversely, if they stayed still and the soil had to move past them, there would be a resisting force on the soil for that situation. And that is essentially captured by these coefficients NQ and NC. So NC captures the component of lateral resistance due to cohesion, and NQ captures the component of lateral resistance due to friction, and will be dependent on the prevailing normal stresses at that particular point. Now, classical limit equilibrium analysis of reinforced soil ignores these terms. Generally, it's been shown that they don't contribute a huge amount, and there are reasons why it's conservative to ignore them. So if you want to replicate classical analysis, then generally I would set them to 0, or just very slightly above 0, as I said earlier, to prevent these nails from floating out. If you do want to model that capacity, because it is there, you can increase those numbers. You basically be looking to use formulae from pipeline or piles, which look at lateral movement of these things through soil, and then you can calculate the coefficients from that perspective, and it will give some additional resistance to the system, but one has to think about the ultimate limit state and displacements required to mobilize these kind of resistances and so on before putting them into the analysis. Okay, so I hope that has answered that one. Got a question about geogrids and facing elements. So let me just bring up one of the wizards. So in the software, you can run there are some built-in wizards which allow you to generate predetermined geometries for fairly common problems. So here we have a case where we've got effectively modelling soil strips behind a wall made of facing panels. So each one of these is effectively a concrete facing panel. And to connect the reinforcement into the panel, we have one type of reinforcement here, modelling a one-dimensional strip, and then another reinforcement there. If I look at its properties here, effectively we just have infinite pull-out, infinite lateral factor. If it's embedded in a rigid material or a very strong material like concrete, it's not going to pull out, so it's rigidly fixed. And any engineered element that connects to any other one are rigidly connected. So basically, in this situation, we've got a connection between the reinforcing element and the facing panel. We can do an analysis. So here we've got a fairly global failure, and you can see the tensile stresses in the reinforcement building it from zero from the free end, but they don't fall to zero at this end because they're connected into a panel, and the panel itself is obviously experiencing a lateral earth pressure, and so that is going to be determine the tensile stress that we see at that point. So that is how we would connect geogrids and facing elements. Okay, I think that has taken us to the end of the webinar, so I hope you found that useful and informative, and I will pass back to Tom just to wrap up. Thank you very much.
Thanks, Colin, and thanks to everybody for joining us today. We do hope you found the webinar informative, and as I mentioned at the start, if it has prompted any questions that haven't been answered within the webinar itself, then please do get in touch, and you can do this via telephone, or if you email support@LimitState.com, we'll be more than happy to help with that. If you'd like to watch the webinar again, or if you feel that you know somebody who might actually be interested to see it themselves, then we'll be making a recording available in the next day or so, and we'll email you with a link once that becomes available online on our YouTube channel. Please look out for any event notifications as well for other webinars and events that we'll send out via email and also post on LinkedIn and Twitter. And yes, finally, I'd just like to say thank you all again for listening, and hope you can join us again in the new year for one of our future sessions. Goodbye.